Welcome to video 7. Video 7 is going to be a little bit different. We're going to focus on the magnetic field, the field structure of nature, literally. So that's why we're showing this this particular thread at the moment. This was started back in August of 2019. This is something I've touched on many times before. You'll see on my HiIQ website I've been showing images like this for many years, upwards of about 11 years or more. So I just want to show this. This is a very important stage. This is where we're at, and this video will focus on exactly what's going on here. We have experiments where we can prove that the magnetic A vector potential here is real, is there. The only explanation for what is going on is the magnetic A vector potential. The magnetic flux, as we know flux, all of it is contained inside the core. There's less than 1% that would leak out on average. So all of the magnetic flux is contained inside the core. These arrows here are meant to indicate current. The current is in the same direction. You'll see here, see the arrows of the magnetic A vector potential. So the current on the core is the same. Okay, so our current is causing, if you like, if you want to call it a tornado, okay, the change of current is causing, if you like, a tornado, which is a magnetic A vector potential that has curl. This is the curl that goes around in a circle. And that's all around and outside the core. Okay, it's provable. We've seen many experiments. It's provable every day of the week. Now this is my theory, and from my experiments I have seen a block wall. Many people disagree with that. That's from my experiments, from my work. I have many experiments that can show, that can prove, that can show that there's something going on there, and that's every single day of the week. There's always a block wall. Okay, so this is about the core. This is something that we want to think about the core. We want to think about the direction, remembering that our right hand grip rule follows the same principles. Okay, so north field up here, if we were to curl our fingers around that way, okay, again the A vector potential has curl, so if we curl our fingers around there, then our thumb will point in the direction of the North Pole. Okay, this is conventional current again, conventionally, and that's what I'm trying to sort of show here, is the conventional current, conventional magnetic field. Old school rules, which we all know and remember from high school, at least anyway. Remembering that old school has been proven wrong in a few areas. Okay, I already know all about that. I follow science pretty solidly. I already know that some of the old school rules are not correct, but I'm not going to confuse people. Okay, there's no point confusing people because it really evaluates to it just as a zero video, so there's no point doing that. Okay, so magnetic field contained inside the core. As long as the magnetic field is changing, there is a magnetic A vector potential. The magnetic A vector potential has curl, exactly the same as the current has curl, okay, and that's around the core. You can measure it, you can do the whole lot, it's all there. Okay, remembering what we're looking at up here is a 3D structure. So what we would effectively see up here would be the wave fronts. Okay, so this is a wave front. Remembering from our previous videos, this travels very fast. We're talking nanoseconds, so it travels very fast. The structure is 3D, so it's around the core in a three-dimensional shape. Okay, the North Pole up here, so if you want to imagine sort of a donut with something's going on in here, this is meant to represent the block wall. Okay, it all has a curl. These arrows here are meant to represent the curl going around. but the effective shape here, if you like a dual toroid shape, pretty much is what we're sort of looking at. Okay, south pole down here, obviously the curl around here as well. There is something going on the block wall. Many experiments can prove it. This is one of them. If you want to go and have a look. Now the double toroidal vortex principle has been theorized by many people, many very smart people. Some very smart people out there have, in my opinion, presented enough evidence to prove it as fact. But again, some people don't want to jump on the bandwagon and don't want to accept the proof that's out there because it's too hard or something, I don't know. Again, we saw this in our last video. This is the dual vortex. Okay, so you can see that there's red out here. Okay, it sort of comes in and is a vortex shape. Remembering up here is the source of red, so the red has been poured in through here. So as we've got spinning around this dual vortex here, one spins one way, one spins the other way. Okay, we have gone through that. We've covered it somewhere. We'll see if we can find it. Now each one of these spins, I think from memory it's inwards. So if you want to imagine a curl going in like that, and then on this side a curl going in like that. Okay, so all the water is being passed through that way on this side, being passed through that way on this side. You can see the vortex from this one over here. So remembering this blue over here has got a different spin. The spin's different. Okay, but they meet and one comes up through the other. I mean, you can see the blue pretty much sort of up to about there. So they sort of meet pretty much in the middle. I mean, you could even say this bit here might be blue. So it's an amazing video. Go and watch it. Study it. It's worth knowing about because this here alone, this video here alone is astounding. It's an astounding video. It really is. Okay, so remembering we've got spin, we've got curl, we've got the whole lot. We've got two sources. So you could effectively say that this might be a north pole up here. This might be a south pole up here. We've got the same spin in the same direction. Oh, look at that. See, something I've already said. Same spin, same direction, a different pole. It's a different, the south pole, the south pole half of the magnet, it's different. That's why they color it different. Red pole, red is the north pole, it's different. Okay, so same deal here. Okay, remembering it's got curl, curls are going in the same direction. Okay, so they're all going through that way, and it's amazing. This is physics girl. She's a very smart girl. You can actually see the spin there on that one. See there? She's a very smart girl. This young lady. She's and she's very pretty too. So go and have a look. Again, this is a tornado. You can see there is definitely a dual spin here. Okay, this spin coming up from the top, and this spin amazingly coming up from the ground. They meet in the middle. Okay, it's everywhere in nature. If you study it, it is everywhere in nature. Anytime you see spin, there's an equal and opposite associated spin. If you like a monopole, you could say it's a monopole. It's all about the spin, the curl, I should say. Curl is not spin, spin is not curl, but I do get the two mixed up, so I apologize. This is where the video was from. Fantastic video. Can't remember where I got it from. I do apologize. This is Howard Johnson's work. Howard Johnson predicted the same. There'd be a south pole down here, a north pole up here. I don't know why, but in my opinion, he's got the arrows the wrong way, but I'm not going to argue with Howard Johnson. The standard view of a magnet here, and Howard Johnson's view of a magnet up here. Howard Johnson is a very smart man. Had a couple of guys working with him. Did a lot of work. Very smart man. Okay, this is another picture that I just think is fantastic. Under this, there is a magnet, a long neodymium magnet. So the one pole up here, one pole down over here, same sort of deal. You can see from the pole, okay, the magnetic flux. Okay, the magnetic flux comes out in spikes. Now there's a very good reason that you see spikes from the North Pole or the South Pole. The reason is the magnetic field is, the strength of the magnetic field is the inverse square law. Okay, so the magnetic field itself, because of this ferrofluid, this black stuff here is ferrofluid, it's magnetic, but its strength, or the strength of the magnetic field from the magnet, is only strong enough to make spikes of a certain length. Okay, so the inverse square law of the magnetic field says, okay, I can only get you up to there because I'm not strong enough to get you any further. Now if you look at these spikes here, especially over here, and the reason I put this picture up is the spikes actually are curling in. So this bit here is the block wall of the magnet. So we're seeing a very similar deal to what we see here. Okay, this is some research that's been done, shown for years. People still even now dispute it. And look at the shape. It's a dual donut. Okay, and it's everywhere. You'll find it everywhere in science. Look again, these are all the hurricanes mapped of the world. Okay, so all the hurricanes in the world, they all either stay in the northern hemisphere, and they track, most of the time they track from the equator line here up. Okay, so they move up towards the pole, or if they're in the southern hemisphere, they normally start close to the equator line there and move down. Okay, that's why everything's moving down. That's why the reddest bits are down the bottom, and then that's why they track up like that, and there's less red at the top. Now the most interesting thing about this picture is there's not a single hurricane ever recorded, and it's an astounding fact. There's not a single hurricane ever recorded that crosses the equator. Never, ever crosses the equator. An astounding, absolutely astounding fact. And why is it not going to cross the equator? Is because the spin is opposite. Now I'll show you that because you'll see it here. So you can see here the magnetic field lines into the Earth. If you were to view the Earth the same as the ferrofluid with the magnet inside it, and if we were to use the right hand grip rule for the magnetic field lines, we would see the same thing. Now this is a complex subject because science tries to explain this away as I forget now, it's called the Coriolis effect, but there is a scientific explanation, and what they tried to explain it with is actually the spin of the Earth. Okay, so the spin of the Earth moves that way, so they do have a reasonable sort of idea on what's going on here, but they're not accounting for the magnetic field. Okay, so if you were to compare the Earth to this photo here, okay, and each one of these spikes, so each one of these spikes on the top half and each one of these spikes on the bottom half of the ferrofluid with the magnet inside it would equate to this here. So each one of these would be one of the spikes, and they're all got different spin. They can never ever cross the equator because the spin is different. They all spin in that way, and that way they spin in that way. Okay, southern hemisphere we get clockwise hurricanes. Northern hemisphere we get counterclockwise hurricanes. Okay, remember the northern hemisphere is actually, and the reason that our compasses point a north pole, which actually is a north pole on the compass, the reason it points a north pole to our so-called north pole is our north pole is actually a south pole. Okay, and that's something else that conventional science has got wrong. I'll show you a video very quickly, just a very short portion, otherwise you're going to get copyright, so just hang with me for a minute.
The magnetic field is created deep in the Earth's core. It streams out near the South Pole. loops around the planet and then runs back into the core near the north magnetic pole. This is the Earth's protective force field. Without it, we'd be in trouble.
Alright, so that's Nova, Magnetic Storm, Earth's Invisible Shield. Great video, worth going to have a look. You'll notice that it said it streams out at the South Pole and back in at the North Pole. The reason that they say that is because they've got the poles reversed. So if you do your research, you'll find out that the North Pole is actually our South Pole, South Pole is actually our North Pole, and it's because we got the magnets on the compasses back to front. We've got to remember the equal and opposite attract. So if we've got a compass with a North Pole on it, then the North Pole will be attracted to the South Pole. Okay. Useless little bit of information, but anyway. Now, Coriolis effect. Go do a little bit of research. This is fantastic. Okay. Again, the spin. So in the southern hemisphere, if you put water into a pail, and if the pail is set up right, once you put water into the pail and then you actually let the water out, the water itself will get a spin on it. Okay, it's like the water going down the toilet. You've all heard of that. Okay, so the spin will be different depending on whether you're on the North Pole or on the South Pole, which amazingly is exactly the same as the hurricanes. Okay, you're going to see the same effect, the exact same effect. Okay, water will go one way, the same as a hurricane does in the southern hemisphere. Water will go the opposite way if you're in the northern hemisphere. Okay, and remember that water is draining down. Okay, you got to remember, without the draining down, it doesn't work. Okay, so hurricanes, exact same situation. We've got hot air rising, cool air dropping. So as the air cools, okay, it drops really fast to the planet. Hot air rises, remember, so the opposite is true of hot air. And obviously as hot air rises or cool air falls, then obviously we get a spinning effect, exactly the same situation. Do some research, because I think there is a lot of information, a huge amount of information about hurricanes that is wrong. Okay, and obviously simple experiments like this can prove it wrong. Okay, again, back to our Earth, hurricanes, you know, I mean, honestly, it's not hard to sort of try and tie these situations together. You can see there's a spin, you can see there's a magnetic field, the whole lot. Okay, this is something else, just a very interesting theory that I have believed in for a long time. It shows that there is a neutral plane in there, very similar to the magnetic fields we looked at before. Extraordinary bubbles. This is amazing. Whales, dolphins, all that sort of thing blow bubbles in the water. These bubbles turn out to be half a toroid. Well, it's a full toroid, but it's half the dual toroid. So interesting, worth going to have a look. So anyway, this thread is it's pretty interesting. Again, they show here the pink bit says it all. Okay, you got spiraling in there. Okay, and it comes out, and that's the flow. Now, water in the pail, if it falls through the pail, depending on what hemisphere it's in, then it does the same thing. Okay, you've got to remember we're looking at a spinning, the curl, if you like, here that we're seeing. The helix, if you want to call it a helix in here, is a very, very important part of nature. So again, that's just the evaporation, that's not a huge amount. Worth going to do some research. Okay, this again is a very important video, or at least part of a video. I think I referenced it there somewhere, maybe that one. This is a neodymium magnet, obviously. It's stuck to a press, and what they've done is they've slowly lowered the press down until the ferrofluid that's down here has been able to be sucked up. So the ferrofluid is stuck to the magnet, but you can see it's only stuck to that top bit, okay, which confirms, if you want, confirms Howard-Johnson's spin on the poles. Okay, so a magnet would effectively be a dual toroid, and this is part of what we could say would be proof that the ferrofluid only sticks to the top portion there. Now, if it was true, if the magnet was fully enclosed by magnetic field, then the ferrofluid would go all the way up. Okay, the first thing any magnetic material is going to want to do is enclose on the poles. Okay, so what we're looking at here is whether people want to admit it or not. The magnetic field is a dual vortex. South pole's a vortex, the north pole's a vortex. Okay, the vortex want to enclose up here on themselves, but they do. You can actually see that they do enclose on themselves up here like that, but they have their own little bits that want to close on themselves in here as well. Pretty amazing. Now this one is a little bit tricky. Let's see if we can zoom out just a little bit on that one. Howard Johnson predicted his magnets like this. Now there is an element of thought we need to probably sort of think about, because if we were to take a single flux line, okay, that would represent a single flux line from the North Pole, okay, field pointing out. Down here we have a single flux line from a South Pole, okay, South Pole moving up in. Then the spin or the curl that we have, because remembering that every time a flux is present and changes, we have an electric field when we have the magnetic flux cancel. Okay, so we have one magnetic flux going that way, and we have one magnetic flux going that way. So this region in here should be a pure electric field. And that is what I theorize creates the block wall. Okay, the region in between the poles, pole here, but the region in between the poles is a pure electric field, and that's why we see the flat bit on the ferrofluid above, and that's why we see no hurricanes ever cross between here, between the equator. The equator on the Earth would be here, through that way. We never ever see it cross between the equator. No hurricane has ever crossed across the equator. The magnetic fields cancel, the spins cancel, and it creates an electric field. So there is no magnetic field in here, even though there is, but the magnetic field cancels. Tricky, again, which confirms Howard Johnson's. The only thing that I disagree with is he's got the arrows at the bottom on the South Pole in the wrong direction. Again, same deal here. So electric field is right in the middle here. That's an electric field, not a magnetic field. Okay, these spikes here represent all the flux lines coming out, trying to enclose on themselves, but they don't. It's a dual toroidal field here, one from each pole. Okay, I think that's probably enough. Maybe you go and have a bit more of a study on it. This is just a very quick bit here. We'll zoom in back to normal. This is just a study on the magnets themselves. So this is a cobalt magnet. This is the electron structure. So remembering the electrons, or free electrons if you want to call them that, are the ones that create the magnetic fields. Okay, so the more electrons, the more charge in the magnet that's able to be aligned, the stronger the magnetic field will be. Strontium, okay, so you can count the electrons, go through, count the electrons wherever they are. Atomic radius, protons, neutrons, positron, electrons. So you can go through, count them anyway if you want. They're normally equal, so positrons and electrons are normally equal, not always, but normally equal as far as I understand at least anyway. Barium, neodymium, go through, count, we've got 60, 56, 38, 27, Okay, just comparing these numbers alone and knowing the fact off the top of your head that neodymium magnets are much, 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 much stronger than what the likes of barium, strontium, cobalt, and all them are. It's because there's more charge carriers in the structure of the material itself. Neodymium carries a much higher charge. Again, magnetizing some, it looks like ferrite magnets there. So this is the electron spin, or the curl. If you want to call it curl, it's the curl. This is a pretty cool experiment to do with magnets. If you want to see free energy, this here, right here, is free energy. What's holding the magnet up? Nothing. I'm not putting in any input whatsoever to the magnet. There's no input at all. What we're simply doing is we're balancing the spin on this top corner of the magnet against the spin on this top corner of the magnet. So what we're saying is the two spins can't go, like the equator. You could say that if you wanted to, you could say there's an equator between here, okay, which would represent the block wall. Okay, and what we're saying is this magnet here, the weight of this magnet is being overcome just by the spin on this magnet over here. Okay, so very, very simple, very easy experiment to do. I highly recommend it if you want free energy. This here, right here, is free energy. The weight of that magnet is being suspended simply by a magnetic field. It's absolutely amazing. Again, just the patterns, if you like, that can be imprinted on. In this case, it looks like perhaps a boron ring or something like that. This might be for a very small motor, so they might have a motor that might be zipping around in there. Again, spin around the wire. It's all about the curl, the spin, whatever you want to call it, the current. It's all about that. Okay, so we want to really imagine every single core, once it's being magnetized, as having the very same curl, the very same spin, the very same vortex, if you want to even call it that, as the current. Now this case here, what they're doing is they're saying this is the wire and this is the current, and this is the blue. In blue here is the magnetic field. Magnetic field and the current is always at right angles. There's always a 90-degree between the current and the magnetic field. Okay, so current, if you wanted to draw a straight line, current going that way, magnetic field going that way. Okay, always a straight line, and it just goes around. However, it depends on your point of view as well. So current always follows the wire, okay, and if you use the right-hand grip rule, the current will always follow the wire, but it depends on what arrow here that you want to use for either your fingers or your thumb, because there's two ways to do it. You can do it two different ways. Not a biggie, anyway. Again, smoke rings. Smoke rings are another unbelievable thing to look at. They travel through the room at a velocity that leaves the pipe, if you like, over here. The velocity doesn't appear to change all the way across the room. These things travel so smoothly, so efficiently, absolutely amazing, 100% amazing, absolutely. There's some really good videos there. I really highly suggest go and watch it. Smoke rings made from a man-made, I can't even remember what it is, man-made something anyway. It's just like an attraction people go and look at. Very interesting. Not a topic that I like. Atomic detonations, same thing. We have a force going up through there, creates a ring which has curl in it, same deal. So you could say the magnetic field might be the actual line here, okay, and the A vector potential is here. It's everywhere. It's everywhere through nature. If you go and study it, it's everywhere. What you'll see and what you'll find is exactly what we've seen. Even jellyfish. Okay, jellyfish tend to take the same shape. Again, the smoke rings, very little loss. There's no loss. Again, more smoke rings. Worth going to have a read. This thread's absolutely amazing. Alright, what we're going to do is we're going to do a few little experiments. Okay guys, this is just a simple circuit I've set up. I'm going to show you something here that is along the lines of what we've been learning for some time. Duty cycle is now 10%. Okay, 10% is something that I've sort of said for a little while now. I think 10% is fairly important, at least to start. Drawing 100 milliamperes from the DC supply. As we turn it up, so what we're doing is we're turning the input voltage up, and what we're doing is we're getting much higher output here now, just for a little bit of extra input current, but the light is much brighter. But look at what's going on the scope. The scope is showing us a waveform that we're all pretty familiar with, and to be honest, if we can go up a little bit more, now that's 12 volts there now, and you can see the scope's pretty, excuse me, or see the scope's certainly giving us a waveform that we really like. What we're doing is we've got the switch in here, a bit of trigger, so our 10% you can see from here to here. Okay, our coils are racing up as far as they can, and then they're dropping down. So this is the drop down here. This is the sawtooth waveform. Up here is all off. All the current in that sawtooth waveform is being generated during the off time. So the off time here is a part of the cycle that we can use to generate excess current simply by conducting at a certain time. I'll put the circuit up so you'll be able to see the circuit here now. Very simple circuit. Now what this is showing is that the currents and the magnetic fields are interacting together in the same space, but with different polarities. So we're seeing one forward current, one backward current, and then one forward current again. So in the system we're seeing a 1, which is the forward current, plus -1, which is the negative current, plus 1, which is the current again that's forward, equals 1. So we have an overall gain in the system. Now this system's not optimal, it's far from optimal. The frequency is 3 kilohertz. The duty cycle is 10%. We're using 2 diodes in the circuit and 3 coils. So what we've introduced now is down the bottom here we have an extra coil on top. So the coils are like this, and we've wound another coil on the top. I think roughly off the top of my head, I think it was about 20-25 turns. The gauge of the wire is not quite 2mm, it's about 1.6 roughly. That is now our input coil. We still have the output over here through a diode, through the light, and we have a diode on this coil up here. Okay, so what we've done is we've found the sawtooth wave. It's not optimum. Certainly this circuit can be made a lot better by fiddling with it, but we have what we're supposed to get. This is perhaps one of the most successful circuits that we've seen yet out of all of our experiments. All of our experiments have led to this, and what we've learnt through the experiments, through 6 videos previously, has led to this. Okay, you can see there that we have a lot of noise. First of all, we have on the scope what we're supposed to have on the scope. generally this is a very successful circuit. Not the cleanest circuit in the world, but certainly a successful circuit. You can see we're measuring current. This is the current. So we've got a big sharp rise in current, rises, and then it decays over time. Remembering this is off time up here. So the input coil is not even on. This is all off time. But we've got a decay in current over time. Okay, so that's current coming out of the system when the input is off. And that's absolutely critical. It's critical to understand this. Once we get to the point where we understand this much about the coils, and once we can get a circuit like this running with minimal effort, then we can concentrate on making it better. Okay, because everything prior to this, everything that we've learned has been a hurdle that we've had to overcome. There's small problems. So I hope this video is useful. Everything that we've explained on our website for the last several years and everything before that has sort of led up to this point. We have a very simple, this is extremely simple circuit and arrangement of coils which works. It just works. This is how coils are supposed to work. Anyway, this is what you really want to look for. So again, in the circuit we've got 1, 2 diodes out to the measurement. This is the measurement resistor out to a load, and we've got 1, 2, 3 coils. So this is an asymmetrical system, an asymmetrical transformer. The input coil is only on 10% of the time. All the rest of this falling current is due to the coils interacting together. So this coil here and the coil down there, the light's being powered from this coil over here at the moment. All we have is a diode on that coil. So that coil just has a diode on it, simple, quick and simple. Diode on this circuit, pulse the input, the bottom coil conducts. As that coil conducts, this coil conducts at the same time, and that's the ramp. So if we zoom in, so you can see this is the ramp time. And we've been through this before in other videos. So what happens is when the coils slap together, the two coils climb in amplitude, and then as they get to the peak voltage, the conduction is at maximum. The input then is switched off, so up here it's off, and then we see a decay over time. So everything that we've led to from the last 2 years, this is it, guys. It's that simple. Okay, we need to make sure that we don't overcomplicate things, that we treat each problem as simple as it possibly can be, break it down to the smallest possible components, and then solve those components one at a time, like we've tried to show in the last 6 videos, this video being the 7th, and we've shown exactly what we need to start looking for. This is the key principle here right now. This is it working. This is exactly what we all need to aim for. Okay, and then it's just a case of just improving it from here, finding the best frequency, finding the best duty cycle. Okay, we have a system right now that is generating current when the input is off. Okay, there's no system out there that I know of that would do this. This is the only system, and this is what I've been showing you for the last 6 or 7 years or so. And certainly 2011 was the start when I first started exploring this, and what I found was pretty amazing. And this is it, guys. This is what I'm showing you. This is the the complete answer, and it is this simple. It truly is this simple. Anyway, I just want to say, if this video has helped you, please consider a donation. This helps keeps the lights on, if you like. Helps keep our wheels spinning.